Hey guys, so today we're going to be in section 4.2, which is logarithmic functions. Section 4.1 was exponential functions, and so this one is logarithmic functions, but we're also going to have exponential functions, and you'll see that here in just a second, because we're going to convert between logarithmic functions and exponential functions. So first, let's figure out what is a logarithmic function. Well, it says for x greater than 0, and b greater than 0, but where b is not equal to 1, then we know that y equals log base b of x is equivalent to b raised to the y power equals x. That means they're equal. If it's equivalent, they're equal. That means we can go from a logarithmic function into an exponential function. So here is the logarithmic function written out. And then here is the exponential function written out. And when you have a log, you have a base. That base is also the base of your exponential function. So here's kind of a neat little wordy thing that I say, and that most people say to help keep track of what becomes the base and what becomes the exponent when you're trying to convert back and forth. It's the base becomes the base, the answer becomes the exponent. So if you look, when we go from log form over to exponential form, the base of our log becomes the base. The answer, which is y, becomes our exponent. So the base becomes the base, the answer becomes the exponent. Just like that. So hopefully, then if I give you any log, we'll be able to convert it over to exponential. And if I have an exponential, I can convert it back to a logarithmic. This helps us to play around with it and to understand it better. So that's actually what we're going to do first. We are going to write these logarithmic equations in exponential form. So the thing you're going to hear me say probably 10,000 times today is the base becomes the base and the answer becomes the exponent. So for this first example, we have 2 equals log base 5 of x. And I need to write that as an exponent. So the base is 5. Base becomes the base. The answer, which is 2, becomes the exponent. And then what's in here is our new answer. So 5 squared equals x. Now, don't evaluate that. Don't say, well, that's x equals 25. That's not what it wants you to do. It just wants you to write the logarithmic form into the exponential form. So you don't need to simplify it at all. Okay? So let's look at b. We have 3 equals log base b of 64. So the base of my log is b. So the base of my exponential is b. The answer will be my exponent. So the answer was 3, so my exponent is 3. And then I say equals, and that equals whatever is inside of my log, which is 64. And hopefully you can see how this can be really nice for solving some of these logarithmic equations when you may or may not have a calculator or know how to type this stuff in. If you can get it to exponential form, sometimes it's easier to solve. So in this one, we have log base 3 of 7 equals y. So they flip-flopped our equation on us, but it doesn't change anything. Our base is still our base, and our answer is our exponent. So the base in this case is 3. The answer is y. And then what's inside of our log is the 7. So 3 raised to the y equals 7. Remember, if I go too fast, since it's recorded, you get the option of pausing me and continuing to work on your own. There, that way you can still see what we just did. So we went from logarithmic to exponential. So of course, then the next logical thing that they're going to ask us to do is to go from exponential into logarithmic. So remember, it's the same thing that's true. The base becomes the base, and our answer became the exponent, okay? So we have log, and then we have a base in our log. Well, the base is the same, so log base 12. The answer became our exponent, So that means our answer is what's in our log. Going this direction might take a minute to think through because you're going backwards. Base became the base, the answer became the exponent, and that's what was left inside. And so hopefully you can go backwards. That's the best way to check yourself, is to get it in logarithm and then say base becomes the base, answer becomes the exponent. Does it work? And if it does, then you probably did it correctly. So for B, we have b to the third is 8. So the base is still the base of my log, which is b. The answer became the exponent, so that was the 3. And so the new answer, the answer on my exponential is what's inside my log. Log base stays, so it's log base e. The answer became my exponent, so that was y, and then the answer over there becomes inside. So notice on these first two examples, the things that we were doing, we were just going back and forth between exponential and logarithmic. We weren't actually evaluating, we weren't solving anything, we weren't coming up with a number, we were just converting back and forth. In the next example we're going to do, we're actually going to evaluate. And so when we evaluate, we do want to get an answer for what our variable is, or what our log actually stands for. So for these, we have 4 examples. And if you notice, they're not actually, there's no equation, there's no x, there's no unknown thing. It's just log base 2 of 16. Well, what does that mean? So the easiest way to do these so far that we know how is to set them equal to x, and then we can do the base becomes the base, the answer becomes the exponent. So I'm going to say this equals x because we don't know what it equals. We want to evaluate it, but we don't know what it equals. So I'm going to say equals x. That way I can do my base, which is 2, base becomes the base, the answer becomes the exponent, and then the 16 is what it equals. So then you can think through, well, 2 to what power gives me 16? Well, 2 squared gives me 4. 2 to the third gives me 8. 2 to the fourth gives me 16. That tells me then that x equals 4, because it's what do we plug in to make that statement true. Sorry, I'm like totally off the screen for most of this. Okay. So we'll do the same thing here. We're going to set that equal to x. That way we can take the base, raise it to the exponent, and then figure out what our x is. So our base is 7, our base becomes the base, answer becomes the exponent, and then what's left over is our new answer. Now, hopefully this doesn't completely lose you and you remember a little bit of dealing with fractions or with exponents. How do we get a whole number into a fraction if we need an exponent? Well, negative exponents flip. They take our whole number and they turn it into a fraction. So what do we need up here to give me a 49? Well, 7 to what power gives me 49? 7 squared. So 7 squared will give me 49, but I need it to be in a fraction form. So I need 7 to the negative 2 equals 1 over 49. Because what that does is that takes 7 over 1 to the negative 2. And then that would flip it to where it's 1 over 7 squared, which is 1 over 49. So if you're not totally comfortable with exponents, this is going to kind of force you to get there, because you're going to have to learn how to see, well, 7 can go to 1 over 49 by simply saying that x equals a negative 2. Okay. If these are ones that trip you up, if these are difficult for you, on your homework, there's always the option after you answer a question for similar exercise. Click that button. If you click it, it'll give you a new one where it would say 6 to the x equals 1 over 64 or something, or 36 or something like that. So it's a similar process with new numbers. you can hit that button time and time and time and time and time again to get you more practice. That way you can get more comfortable. So I totally recommend that on the My Math Lab. Okay, C says log base 25 of 5, and we're going to say equals x. So the base is 25, x for the exponent equals 5. Well, what do we have to do to 25 to get to 5? Well, you'd have to divide it by 5, but you can't do that if it's an exponent. We can't divide. So we'll basically think about what do we do to 5 then to get it to 25? Well, we times it by 5, right? That's a square. If it's a square, that means we can square root. Now, hopefully from 4.1, you remember how do we write it if it's a square root? We write it as a fraction. That means 25 to the 1/2 equals 5. Because 25 to the 1/2 is the same thing as writing the square root of 25. This is from 4.1, and also we talked about it some back in chapter 1. But square root of 25 is 5, thus our x would be 1/2. And it's okay if you don't see it right off the bat, but that's kind of the logic and the mentality you have to start thinking about is how do I get over to this 5? What exponent can I raise this base to give me my answer? And it's also why I'm working one of every type of example that I can think of is so that I can help you to kind of see and process what's going on. Okay, last one. Log base 2 of the 5th root of 2. Well, that sounds really gross, but it's actually not horrible, I promise. So the base becomes the base, the answer becomes the exponent, and then we have the 5th roots of 2. Now, notice up here, the square root became 1/2. So a 5th root is going to become a 1/5. So we could say 2 to the x equals 2 to the 1/5, right? 2 to the 1/5, just like 25 to the 1/2 is the square root of 25. So now, what is x? Well, if we have 2 to the x equals 2 to the 1/5, then x equals 1/5. So sometimes they're very straightforward. Sometimes they have a negative. Sometimes they're a little bit harder to see. And so you have to practice. You have to practice, and you have to practice thinking about exponents in that way. Thinking about what do I raise this number to get this other number. Here's a couple of logarithmic properties. I'm probably just going to hold it for this one. There's only 2 things. Logarithmic properties involving the number 1. The first property says log base b of b equals 1. We know that this is true because b to the first power equals b. Base becomes the base, the answer becomes the exponent, and then that's what your new answer is. So we know that that's true because of that. It holds true. Same thing down here. Log base b of 1 equals 0. So log of 1 is always 0. And we know that's true because b, the base becomes the base, the answer becomes the exponent. Any number to 0 is 1. Okay, let's move to the back of the room. We're going to do a couple of examples. And then I'm going to have to screen share because the majority of our notes I'm not writing on the board because you can access my notes. And I already wrote them once, and it's a lot of stuff. So, just fair warning. Okay, this example says graph on the same coordinate system. So it gives us an exponential equation, and it gives us a logarithmic equation. And we're going to graph them together so that we can see what happens on the graph. So remember, what I like to do is I like to do a table. Now, usually I do a vertical table. This time I'm going to do a horizontal table, and it's going to make sense in a little bit why I chose to do it that way. So what I mean by that is I'm going to have my x values, and I'm going to have my f of x values, so my y values across the bottom. Remember, I usually choose -2, -1, 0, 1, and 2 as my x values. That way, I get some negatives, I get 0, and I get some positives, and that really is going to give me a good representation of what's going on in my graph. Now, hopefully, you're like, well, 2 to the x, we've done that. We did that twice in 4.1, and it's true, we did. So hopefully, me doing this horizontal table isn't going to trip you up, because you should already know kind of what this graph looks like. It's an exponential graph, and it's an increasing exponential graph. Okay, so 2 to the -2, remember that's when we flip it into a fraction. So 1/2 squared is 1/4. 1/2 is 1/2. 2 to the 0 is 1. 2 to the first is 2, and 2 to the second is 4. Okay, so there's that nice little table. Okay, so I'm going to go ahead and graph that over here to the side. Plot those points that we know. Okay, so we had -2, 1/4, -1, 1/2, 0, 1, 1, 2, and 2, 4. So there's f of x. Now, for g of x, we have x, and then we have g of x. Now, this is why I decided to do it horizontally, because I want to show you the cool thing. We said at the very beginning of this class that the log, like this, log with the base the same, is going to be their equivalent, right? So what we can do, here's the easy thing. Instead of plugging in new numbers, so if I plug in x, I have log base 2 of a number. Well, that's a calculator. It's going to give me a decimal. It's going to be yucky. So here's the really cool thing, though. Because these have the same base right here, and because they are in the same system, watch what we can do. I want to show you something. Watch. We can flip-flop our x's and our y's. We can flip-flop those. So that means up here I would have 1/4, 1/2, 1, 2, and 4. And then down here I would have -2, -1, 0, 1, 2. I can simply flip-flop my top and my bottom and get my new ordered pairs. So what that tells me is at x is a -1/4, I'm down at -2. Or x is at a 4th, I'm down at -2. Is x at a 1/2, I'm at -1. 0, 1. 2, 1. And then 4, 2. Right there. So if you look, they almost, it's like they mirror each other. I wonder what that's called when they mirror each other. If you look, they could lay on top of each other. That means they're symmetric. There's symmetry here. There's symmetry between our exponential function and our logarithmic function, which is why I wanted you to draw them on the same graph together so that you can see that. And that is actually one of the characteristics of logarithmic functions. So I'm going to screen share now with you, with any luck. And a lot of stuff open. Where? I think it's over here. There we go. For some reason, when I scanned this in the first time, it skipped this whole page. And then when I scanned it in the second time, it did this weird coloring thing. So I know it's not the best scan, but it's still a scan. So just like in 4.1, there was characteristics of exponential functions. In 4.2, there's characteristics of logarithmic functions. So some of these are kind of logical, or at least now they're logical based on the graphs that we just did, because the logarithmic function is the g of x one. So it's the bottom function. So if we look at that, does that function ever actually cross the x-axis, or excuse me, the y-axis? It does cross the x-axis, but it doesn't cross this y-axis. So if you notice, if we're looking at trying to figure out what the domain is of this g of x, well, what would the domain be? The domain is going to be 0 to infinity, not including 0 because we don't ever actually cross that y-axis. And if you notice, the way you know that is if you come over here to the negative side, if I pick -1 and I go down or up, I'm never going to hit this graph, am I? Because it's not included in the domain. In 4.1 in exponential, our range was like that, as you can tell. See, they're kind of opposites of each other. Our domain was -infinity to infinity because it goes on forever. There's no x value I can't hit on the exponential. But on the logarithmic, it just goes from 0 to infinity. They're kind of flip-flopped because the range now on logarithmic is -infinity to infinity. There's no value for y that this graph is not going to hit. It's going to go on for forever and ever, up and down. Whereas 4.1 told us that our range was 0 to infinity because with the exponential, you never cross that x-axis. So they kind of flip-flop, and that's kind of neat. So that's characteristic number 1. The domain is 0 to infinity. Characteristic number 2, the range is -infinity to infinity. And then characteristic number 3, our x-intercept is 1, 0. And that's because of f of 1 for log base b of 1 equals 0, which was one of our 1 properties that we did just a little bit ago. So it's really neat because in the exponential, we have a y-intercept, but in the logarithmic, we have an x-intercept. And they're both at either 0, 1 or 1, 0. So that's pretty cool. In logarithmic, we don't have a y-intercept. We never cross, and that's because there's a vertical asymptote at y equals 0. And similarly up here, we had a horizontal asymptote at x equals 0 for our exponential. So I just think it's neat because they kind of mirror each other. They kind of have the same rules, they're just similar. Okay, so number 5, if b is greater than 1, then the log base b of x graph is increasing. Okay, which is what we had here. We had our b was 2, that's greater than 1. So we went from something, it's going up, 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 up. It's increasing. However, if the b is between 0 and 1, so if it's a fraction, then we have a decreasing graph. So I included both these graphs right here on the notes page. So you can see this first one, b is greater than 1, is pretty much exactly what we have on the board for the problem that we just did. When b is between 0 and 1, if you'll notice, it gets really, really, really close to the x or the y-axis up there in the positive, and then it comes and it goes out like that. So it flips. Characteristic number 7 is that the graph of f of x log base b of x approaches, but it does not touch the y-axis, which we've already kind of said. That means that there's an asymptote at the y-axis or at x equals 0. It's never going to cross. Now, like I said in 4.1, that's in the basic graphs. If we do transformations, then there are chances that we're going to cross that axis, but that's because our asymptote is then also going to shift. And so we will always have an asymptote. It just isn't always going to be that y-axis if we're doing any type of shifting, which is what the next set of notes is. So again, remember, you can pause this to write all this down. However, these are the same shifts that we've always done. This is the same shifting that we did in chapter 2 when we talked about regular functions and linear functions and all that kind of stuff. These are the same transformations that we did in 4.1 with the exponential, but now we're doing them with the logarithmic. So I'm not really going to talk through all this. The things to be careful of, though, is like if you look at the vertical shift, that's just where we have the plus or the minus out, and that's outside of the logarithm. That's not included in the logarithm. If that constant that we are adding or subtracting is included in the logarithm, where it's x plus c and it's inside parentheses like it is right there, that's the horizontal shift. That's where it does the opposite of what we usually think it's going to do. The negative shift it to the right, which is the positive way, and the positive shift it to the left, which is the negative way. The c out in front of the log is a vertical shift or shrink. That one I think kind of follows the rules in that if c is greater than 1, it's going to stretch it. If c is a fraction between 0 and 1, it's going to shrink it. Whereas if you have the c inside of your logarithm, again, if it's inside, it does the opposite of what you would think. So if c is bigger than 1, it actually shrinks it. Whereas if c is between 0 and 1, it's going to stretch it. But those are horizontal stretches and shrinks. The ones where it's outside of the log are vertical stretches and shrinks. And then obviously if there's a negative out front or a negative inside, that's going to be a reflection. So there is a table. It is a lot of stuff, but the rules are the same that we've done all year. The rules are the same in chapter 2. The rules are the same for exponentials. The rules are the same for logarithmic. So hopefully it's not so much a stress of like, oh, there's a whole bunch of new rules. Hopefully it's just a practice and a reminder of how to use the rules in this new function. So I am going to show you 2 more examples, and then I will also screen share. I'm just going to leave the screen share up, but I'm also going to show you one other little general property thing about logarithms. So we're nearly done. Okay, I told you the characteristics of a logarithmic function, and I told you the domain of logarithmic functions, yeah? And I told you the domain is 0 to infinity. But I also told you when we start shifting things that changes. So here's the little note. I said the domain of a logarithmic function is 0 to infinity, but if you do a horizontal shift, then the domain will also shift with it. And that's because we're shifting our whole graph somewhere on there, which shifts our asymptote, which is what I was saying. The horizontal shifts are the ones that are included inside of the parentheses. So I've given us 2 examples so I can show you what I'm talking about. We have f of x equals log base 4 of x plus 3. Notice that plus 3 is inside of the parentheses, so that tells us it's going to be a horizontal shift. Now, like I told you, the horizontal ones kind of, they do the opposite of what we think. So this is a plus 3. So plus we would think positive, which goes to the right, but because it's a horizontal shift, it's actually going to go the opposite direction. So it's going to the left 3 units. Okay, so think about what our graph was. Our graph got really close to the 0, right? To that y-axis, but it didn't ever cross. But now we're going to shift everything over to the left 3 more units. So what do you think our domain will be? If we shift to the left 3 units, then our new domain will be -3. to infinity. Because what we did was we took our graph, which looked something like this, and we took it over 1, 2, 3 spots. And so now our asymptote's there at -3, and it's going to do this. So instead of getting really close to 0, it's going to get really close to -3, but it's never going to cross it. Thus, we don't include it. We use a parenthesis instead of a bracket, but it's going to go from -3 to 0 or to infinity. So hopefully, if this makes sense, then you can tell me what's going to happen on the next one. For g of x equals log base 4 of x minus 5. Again, this is a horizontal shift because it's included in the parentheses. That is a minus 5, which means we're going to go to the right 5 units. We went to the left 3 units. Now we're going to go to the right 5 units. So my domain will be 5 to infinity. These problems will ask you find the domain, and then it'll give you some sort of a horizontal shift, and it wants you to be able to identify how that messes with your domain. Now, word of caution, make sure it's a horizontal shift. If it gives you g of x equals log of 4 of x and then minus 5, sorry, that ran right into that, but like this, and it doesn't have that in parentheses, then that's not a horizontal shift. That's a vertical shift, and that tells you we're going to go up and down 5 units. But that doesn't do anything left or right, so that doesn't actually affect our domain. So you need to make sure that the transformations that they are asking in the problems are actually horizontal shifts. If they're not a horizontal shift, it doesn't affect your domain in this case. So be aware of that on your homework. So here's the last, it really didn't copy well. Sorry about that. Here's the last couple of properties. And there's 4 properties, and then it shows you what they are in common log, which is base 10, which if you see something that's written log 5 equals x, and it doesn't show you a base, the understood base is 10. It's kind of like this x over here. We don't write that there's a 1 out in front of it, or the square root of 2. We don't write this little 2 out here because it's just understood. So the common log is a base 10, and we don't write a little 10 there, but that's what's there, okay? So there's common log, and then there's the natural log, which is going to be base E. Base E is whenever we use what's called ln, which is known as the natural log. It works exactly like logs. We just use a different designation for that so that people know what that is, okay? Because like with log base 10, we don't write that little 10. Well, with ln, we don't write the little e, and that's why, is because it's understood that it's there. Okay, so the first property says log base b of 1 equals 0. We've already had this property on the front board, and what that means is that log of 1 equals 0, always. ln of 1 equals 0, always. And that's because if you think about the base becoming the base and the answer becoming the exponent, anything raised to a 0 exponent is going to be 1. So that's that one. Log base b of b equals 1. Again, this was the other, this was actually the first property that I did at the front of the board. And that's because the base becoming the base and the exponent becoming the answer becoming the exponent, we'd have b to the 1 equals b. Okay, well, that's always true. 10 to the 1 equals 10. E to the 1 equals 10, or e to the 1 equals e. Anything raised to the 1 power is going to give you itself. That's why this second one is true. Now, this next one, it says log base b of x equals x. So that's pretty cool. Basically, you have the same base as you do what's inside, which means you have x equals, then you just have that. Like, it doesn't really do, because the base becomes the base, the answer becomes the exponent, you're left with what's left over. So it just equals x. because it's going to go away. Log b of x equals x. Base becomes the base, answer becomes the exponent. B to the x, b to the x. It's really small. I don't know if you can see that. Basically, all of these things are true because of the base becoming the base, the answer becoming the exponent rule. These are just nice little properties to know because when you go later on in this chapter, we're going to be simplifying and solving logarithmic equations, and we're going to need to expand and condense, and this helps us to do that. So here we have b raised to the log base b of x equal to x. Again, very similar process here. So that says 10 raised to the log of x equals x, and e raised to the ln of x equals x. These are properties that are just true for all of our logarithmic functions, and so they're good to note because they're, like I said, they're going to come in helpful later on. So that is 4.2. Hopefully it's not too difficult. It's very, very, very similar to 4.1. So if you didn't have a good grasp on 4.1 with exponential functions, hopefully you got a little bit more practice with them here in the logarithmic functions, and you understand how they interact with each other. Hope you have a good day.